All right, we're ready to get started. So, in our last lecture, this is what we end up with, right? So, in our last lecture, remember, I hope that last lecture was like a connecting all the dots lecture, meaning like for a closed system, PV work only, equilibrium, so reversible PV work only. We started from our 6 basic equations. Now, the first one coming from first law and second law of thermodynamics. So U equals to Q plus W, and also dQ reversible equals to TdS. All right. So from our first law and second law of thermodynamics, that's our first basic equation. And then we have a bunch of definition come align with that basic equation. So this is equation sheet I made. You feel free to make your equation sheet. I'll also upload it later on. Now from these 6 basic equations, and the calculus toolbox that we were discussed, like everything in the calculus toolbox are very straightforward, right? So dxy equals to x dy plus y dx, how to write the total differential of a, like z as a variable of x and y, and also the Euler's reciprocity rule. So using these calculus rules, we end up deriving a series of equations. So we have our Gibbs equation telling you du equals TdS minus PdV, and then using the definition of enthalpy, Helmholtz energy, and Gibbs free energy, we went on to derive the set of Gibbs equation. Then, by writing out the total differential of each Gibbs equation, we end up finding relationship between your thermodynamic state functions and some of the partial differential equations. And then, from here, again, back to the Gibbs equation, using the Euler's reciprocity rule, we end up getting a series of Maxwell relations. And observing the Maxwell relations, like the importance or the beauty of thermodynamics is that using these calculus rules, we will be able to measure, for example, like how does some of these abstract thermodynamic state function change. You can build a relationship between, for example, ds over dp at constant t to be equal to the negative of dv over dt at constant p, which is something we can actually measure in reality. And just as a reminder, I brought up some of the measurables. So basically, relationship between your temperature, volume, and pressure. If we play it carefully, we can also find scenarios where your internal energy or enthalpy is kept constant. So that's our Joule experiment and Joule-Thomson experiment. So these are the differentials or the measurable properties that scientists have. All right, so this is connecting all the dots. So last lecture, we did all that. You should be proud of yourself, by the way. And then from here, at the end of our last lecture, we went over to write out, let's say, dependencies. Sorry, wrong note. Write out the dependencies of your internal energy, enthalpy, entropy, Gibbs free energy on these variables like volume, temperature, and pressure. Right, so we did this one together, like how does your internal energy change with respect to volume and temperature, and we did this derivation together in our last lecture. And then the change of internal energy with respect to temperature at constant volume is just Cv. Doing the same kind of derivation, you can get the pressure dependence of enthalpy and temperature dependence of enthalpy. All right. And then we also have pressure and temperature dependence of entropy and Gibbs free energy. So these are the things I'm like, have you tried yourself and derive these terms? And I do expect you to know why they are the case. So if you feel like lost in any of these derivations, let me know and we'll clear it out right now. So anyone go back and try that and don't know how to do it? We're good? Okay, sounds good. So today we will be this, again, like in our typical setup for our chapter, right? We introduce the abstract concept, we do all the derivation to come up with expressions of these terms, and then apply these terms to solve real problem. So today is going to be one of those solve real problem classes. So we'll go together and see how do we use the things we derive, like the dependency of the state function on the variables, into solving how does your entropy change along a process, or how does your Gibbs free energy change along a thermodynamic process. And let's see how we do it. First thing first, derivation example. That's our favorite topic. Again, this is one of those topics that I want to go over this with you just to demonstrate in like what's in my mind when I look at this kind of question. Because this is one of those questions, like when you see it, it'll be like, okay, deep breath, I don't know how to get started. For example, it's asking you to show that like the Joule coefficient equals to pressure minus alpha T over chi and divided by CV. You'll be like, what, like how exactly is that related? So in this problem, I'm just gonna go over with you like what's in my mind when I look at this problem. The first thing I do is to write out all the definition of the terms in this expression. Like we have Joule coefficient, pressure just stays as pressure, alpha equals to 1 over V, dV over dt at constant P, chi is negative 1 over V, dV over dP at constant T, and CV is du over dt at constant V. So just write out what we already know. And then things will become slightly more straightforward when we write out everything. Now I'm just rewriting this equation using all the definition that we write out, right? So this will then become dt over dv at constant u equals to, well, pressure minus alpha, so that's 1 over v, dv over dt at constant p over chi, that's negative 1 over v, dv over dp at constant t times temperature and divided by the CV. So I'm just going to write this as the flipped one. So that's going to be my dt over du at constant v. All right, so that's what we're trying to prove. This one we're just writing out what we already know. And some of the things then we can straightforward like cancel them out. Like for example, in this case, we know that volume and volume cancel out. My negative and negative cancel out. And in here, my dV dt over pressure and the dV dP over pressure, this one is related, right? So what we end up getting is this term, or the alpha over chi term, effectively becomes my dP over dt at constant v. This one just using the cyclic chain rule. So you have the product together equals to negative 1. And I think there's a missing minus because we're using the cyclic chain rule. And then we can reorganize it to be dt over dv at constant u. We're trying to prove that equals to p minus dp over dt at constant v times dt over du at constant v. Yes?
There's a t multiplied by that.
Yes, correct. Thank you for pointing that out. And then there are several things. There's one more thing you can look at. So we have these two terms. So whenever you see like three things interconnected with each other, it's a hint of using the cyclic chain rule, because you can always reduce these two partial differential equations into something like we already know, which is, in this case, if we write out everything, we have dt over dv at constant u times dv over du at constant t times du over dt at constant v. And that equals to negative 1. Or from this relationship, we can solve that my dt over dv at constant u So that's this one. Just equals to -1. So -1 divided by these terms. So I'm just putting these as flipped. So du over dv at constant t, dt over du at constant v. Right. And if we're plugging these things back into this equation, then we can see these two will cancel out. And what we end up getting on the left-hand side is my du over dv at constant t equals to P minus temperature times this dP over dt at constant V. And this part, at this moment, I start to recognize, oh, okay, we're just talking about the volume dependence of my internal energy. All right, so on the left-hand side, I only have my volume dependence of my internal energy. So maybe I don't have to write out that alpha and chi, but it's okay. Yes?
What did you write below
This one?
Is that a 0?
No, I'm just highlighting this. I'm just trying to show, like, from this point, I was like, okay, what is this partial differential equation? So on the left-hand side, this is my volume dependence of internal energy at constant temperature. Right, or this is something we already solved in the previous lecture, or what we know is du over dv at constant t equals to t alpha over chi minus p. All right, and this one is just alpha over, so this one is inherently alpha over chi, so that goes back to what we start from. All right, I'm basically going with you, like, what exactly is in my mind with all the mistakes. Like, I don't need to write out the alpha over chi, but it doesn't matter. Like, later on, I'll be like, okay, so that's just the alpha over chi. That's just part of my volume dependence of internal energy when approaching this problem. There are different ways to do it. Obviously, if you are, like, familiar enough with what we're reading, you can also approach this problem by thinking about, okay, so in previous lecture, we solved that du over dv at constant t equals to negative mu j cv. So that's something we discussed in chapter 2 and start from there. That's also a way of solving this problem. So there are multiple ways of solving these kind of derivation problems, whichever works for you. The take-home message here is that whenever you see two partial differential equations with three variables interconnecting with each other, that's a hint of using the cyclic chain rule to reduce its complexity. How are we doing? Doing good? Okay, sounds good. So this is a quick derivation example. Again, I didn't get to the very end, but I'm just trying to show, like, what's in my mind when I see this kind of derivation problem and how to approach it. Next up, now we're in 4.5, which is, okay, now we know the dependence of my internal energy on different variables. What we actually care about is how does my state function changes along a process. Right, so we went over that case by case for internal energy, for enthalpy, for entropy, for Gibbs free energy, for Helmholtz energy in all previous chapters. So now, hopefully, we'll have again, connecting everything together and see, do we have a general solution to solve for the change of these thermodynamic state functions for any kind of change of state at equilibrium when we have, like, closed system, reversible PV work only. So starting from delta S, because this one is more fresh, right? We're talking about S entropy as a function of temperature and pressure. That's in our Gibbs equation. And let's say my initial state is P1 T1 and final state is P2 T2. Again, one might ask, like, why we're not considering, like, P, pressure and volume, or volume and temperature. It's the same. Like, these are connected. Like, your pressure, volume, and temperature are three things connected with the equation of state. So you can also rewrite your P1, T1, P2, T2 into like V1, T1, and V2, T2. Doesn't change anything. Your volume is also changed with respect to the pressure and temperature change. All right, so in here, just to make our life easier, we're just starting from the temperature and pressure. So what do we know about my ds? So when we write out ds, that's why I'm just writing out the total differential of my ds. So that becomes my partial differential of ds over dp at constant t dp plus ds over dt at constant p dt. Now this one, we're just writing the total differential of like dz as a function of x and y. That's dz over dx at constant y, dx plus dz over dy at constant x dy. Just writing out the total differential, right? And in here, there are several things we already solved. Like, for example, this one. That's a pressure dependence of entropy. So that's something either you already solved or you know how to solve. So that equals to negative alpha v. Yes?
What's your thought process in determining why you would first write out the total differential?
This one? Okay, so the thought process is actually following. What are we looking at is delta S. So we're going reverse, right? So what is delta S? Now, delta S equals to the integral of ds. Right, so I want an expression of my ds. Now, that's behind my logic of writing out ds. So in here, getting back to our total differential, we have my partial differential of ds over dp at constant t equals to negative alpha v. Partial differential of s over t at constant p equals to cp over t. So these are all the equations we went over last lecture. And then, well, to get delta S, what are we doing? We're taking the integration on both ends. So what we end up getting is delta S equals to the integration of ds. And we're taking the integral from P1, P2, negative alpha v dp, plus the integration of T1, T2, you got Cp over T dt. All right, and remember alpha is something you can experimentally measure. Not necessarily a number, it can also be an equation. It's part of the equation of state. Cp is same thing, you can experimentally measure. It can be a number if we're talking about ideal gases, or it can be a mathematical expression. So for example, in this case, we can easily link this question into something we already did before. Let's assume we're having an ideal gas with constant Cp. Then we can further simplify this equation for this ideal gas constant Cp, right? For ideal gases, what do we know? We know alpha equals to 1 over v, dv over dt at constant p. And for ideal gases, we can simplify that because we know that Pb equals to nRT, volume equals to, well, nRT over P at constant pressure, and you plug in the numbers, solve the differential equation, you get alpha equals to 1 over T. And then you can plug that in to the mathematical equation there. All right. And now from here, what else do we know? Now, in this case, thinking about both the pressure and temperature are all changing, it's not straightforward to think like, how do I solve this integral? How can I separate these two integrals by only taking the integration over pressure and temperature? So that goes back to our discussion of building a reversible path that you can solve for the change of your state function. So again, this is a review or reminder of something we discussed before, right? So what we discussed before, let's assume we have something. I'm just going to use a PV diagram to indicate like different thermodynamic states. Like if you have an initial state and you have a final state. Now, in this case, we're not specifying how the thermodynamic state change is taking place, meaning from my initial, like P1, T1, to my final, P2, T2, I don't know how things are changing. We can say the real path is like something like this, right? And let's say this is my initial like S1, this is my final S2. Now along the real path, my delta S of this process equals to S2 minus S1, because my entropy is a state function. Same applies to internal energy, enthalpy, Helmholtz energy gives free energy, all right? But for us, in order to solve for delta S, we can build our path the way we want it to be. So in this case, I'm just saying, okay, so I want to keep my pressure at constant. So I'm getting us to like S prime. So I'm talking about my first process is isobaric. At constant pressure. So at constant pressure, this first term disappears, right? So what we're having is from my constant pressure process, we are only talking about my delta S equals to my second term, which is the integration of T1, T2, Cp over T dt. That's my delta S1. And then for our second process, assuming this is a isothermal curve, it may not be, but in this case, let's assume this is an isothermal curve. I know it's not a real isothermal in the PV diagram, but assuming that's an isothermal process. So my delta S2, well, now it's an isothermal process, so this integral will go to 0. Well, temperature is not changing, right? So dt equals to 0, or this one will have dp equals to 0. So my delta S2 equals to the first integration, which is P1, P2, negative alpha V dp. All right. And in this case, the process from S1 to S2, that's the same idea, right? So from S1 to S2, taking my path, we're getting delta S equals to, well, S2 minus S prime minus S prime minus S1. Now this S2 minus S prime equals to my delta S2. My S prime minus S1 is my delta S1. I think this is plus, sorry. All right, so overall, the delta S of this process, you can solve these two integrals separately because we can build these hypothetical paths for the entropy change to take place. Or my total delta S equals to my delta S1 plus delta S2. So far, so good? So now let's look at a specific example that you might see, which is, well, now calculate delta S when now you have numeric numbers, right? You have 2 moles of water going from 27 degrees Celsius and 1 atm to 37 degrees Celsius and 40 atm. Use example 4.2, so I'm giving you this number from example 4.2, and tells you can neglect the pressure and temperature variations of CPM, alpha, and VM. So in this question, we're giving you alpha, CPM, and VM as a constant. All right, so for this kind of question, now we can pretty straightforward to set it up. gonna leave my total delta S equals to delta S1 plus delta S2. So for this question, well, you can do it whatever way you like, but we can start from stating the initial state, which in this case we have P1 equals to 1 ATM, T1 equals to 300 K. So let's build our reversible pathway in this case, or let's build our hypothetical pathway. So let's say my first step, I want to keep my pressure not changing, so isobaric, temperature increase to the T2, which is 37 degrees Celsius. So we get my delta SA, so we get it to my P1 still equals to 1 ATM, and my T2 equals to 310 Kelvin. So for this process, for this first step, we have my delta S1 equals to your T2 Cp over T dt. Cp is a constant, can solve that integration. And that gives me my N Cpm ln T2 over T1. All right, and then we can do the same. Next step, second step, we have my isothermal pressure change to get to our P2 equals to 40 ATM, temperature remain the same, and my delta S2, we're using our first part, which is the negative alpha V dP. Now in this equation, we're assuming the Vm is not changing, we're assuming alpha is not changing, then that you can simplify it to be negative alpha Vm times N and P final, or P2 minus P1. And at the end, you add these two numbers together to get your final total change of entropy. Yes?
So we could technically have the isothermal process first and then.
You can have a, well, in this case, you can have an isobaric change first and then the isothermal, or the other way around. No matter, like, whatever path you take, you'll get the same answer. You can also go very extraordinary of say like, hey, I want to raise my temperature to something else and, you know, drop it down later on just to make your life more complicated. But it's just a demonstration in like what are we doing when we say build the reversible path. All right. Okay, so that's the entropy. Now, if this one is working for you, like the build the path, the same applies to all other state functions, right? If we can build that path for like isobaric and isothermal for entropy, well, likewise, we can do the same for enthalpy, because like entropy, enthalpy is also a thermodynamic state function. It doesn't matter which path we take. So in this case, following that same logic, when we're calculating delta H, right? So delta H, that's the integration of dH. So how do we do it? Well, we first write out what is my differential of enthalpy, dHTP, and that's, well, dH over dt at constant P times dt plus dH over dP at constant T dP. Again, the first one is a temperature dependence of enthalpy at constant pressure. Second one, enthalpy, pressure dependence of enthalpy at constant temperature. So these are the things we solved before, or you know how to solve. The first one is Cp. Second one is negative TV alpha plus V. All right. And what we end up getting is my dH equals to, well, Cp dt minus Tv alpha plus V dP, and my delta H equals to integration of dH equals to, well, T1, T2, Cp dt minus P1, P2, Tv alpha plus V dP. Doing good? Yes.
Should the V be in a parentheses?
Which one?
Or for TV alpha plus V?
This one?
Different, right? Does the negative sign be, yeah, negative?
Oh, yeah. Yeah, that's true. So it's, wait, no, actually, this one is the CPD. I think this one should be a plus in that case. So, quick question here. Why can't we rewrite this one to Cp delta T? Yeah.
CP can be dependent on T.
Yeah, so this one, like Cp can be dependent on T. I know we deal with ideal gases a lot, like assuming the Cp and Cv are constant. Don't make that assumption unless we specify like Cp is a constant. Like this is where we end up with. And given the actual condition, then start to think about, okay, how do I solve this integration? All right, so don't make the assumption and take it out too early, yes.
If we're still working in the same context of the last problem though, could we get rid of this delta T?
Right, because last question we specified the heat capacity is a constant, right? So if the question didn't tell you the heat capacity is a constant, don't assume it. That's the most important take-home message. All right, and then moving on to delta U and delta G. Now we have an expression of delta S and delta H. For delta U, it's actually pretty straightforward, so I'm gonna skip it. You can try the same of writing out the delta U equals to the integration of T alpha over chi minus P dV plus CV dt. So you can try it yourself, it's the same logic. And for delta H, I'm gonna spend a little bit more time in delta G, the Gibbs free energy, because later on we'll use delta G as our handle to make a connection between material equilibrium and these thermodynamic equations. So for delta G, starting from its definition, so we have G equals to H minus Ts. All right. So if we're thinking about isothermal processes, then my delta G just equals to delta H minus T delta S, which is something we discussed before. And in addition to that, we have went over the pressure dependence of delta G. So in this case, when we're talking about constant temperature process or isothermal processes, we have Gibbs free energy as only as a function of pressure. And we know that dG over dP equals to V, or this one is like partial of dG over dP at constant T equals to V, but at isothermal processes, this becomes normal differential equation, thus dG over dP equals to volume. Or the other way to put it is we can write delta G equals to P1, P2, volume dP. All right. And then, now we have two different expressions of delta G for the isothermal processes. And then we want to take this one step further of thinking about a reversible process at constant temperature and pressure, PV work only. So this is a very common condition for chemical reactions. Now you can have a test tube, you keep it in a water bath at constant temperature. The pressure is just atmosphere pressure, and you have reactions taking place in your test tube. So it's a very typical chemical reaction scenario. Now in this case, what do we know? We know that my delta H equals to QP at constant pressure. We also know my ds equals to dq reversible over T, or my delta S for isothermal processes, that equals to my Q over T. So for my isothermal processes, my delta G equals to delta H minus T delta S. Now this delta H equals to QP. My T delta S also equals to QP reversible. Thus, my delta G equals to 0 for the reversible processes, constant TP, PV work only. And hence, that's what we say when we say, okay, so we're using delta G as a criteria of like whether or not your chemical reaction is at equilibrium, or reversible processes only. And let's do one more example together. So that's all the like material in how to set up our calculation for delta G and delta H. But so far we've been working with like alpha in our expression. We've been working with like heat capacities in our expression. The next question is, well, how exactly does it look like in reality when we're not having an ideal gas? So that's our next example. So this one is a more comprehensive example. It's going to be a longer derivation, but at the end of the day, you'll be like, okay, so this is the general way people use to solve for like delta H and delta S. So in this case, we're giving you that a certain gas obeys the equation of state. So the equation of state is known. That's PVM equals to RT times 1 plus BP plus CP squared. In the equation of state, your B and C are constant. The question asks you to find an expression for delta HM, and so the molar enthalpy change, and delta SM, so the molar entropy change, for a change of state of this gas from P1T1 to P2T2. And it's also saying you can assume your CPM as a constant. All right, so this is going to be one of the more challenging problem if you ever see it in your worksheet. Like, so how do we approach it? For these kind of question, well, first thing first, I like to say like, okay, let me just write out what I already know from these kind of question, right? So we read it, we'll be like, okay, so the question is asking for the change of my state functions, enthalpy and entropy. So, well, we went over that earlier today. So we have delta H equals to, well, 1 to 2 Cp dt plus 1 to 2 minus Tb alpha plus V dp. All right, that's something we derived. And also my delta S equals to 1 to 2 Cp over T dt minus 1 to 2 alpha V dp. Now, observing what we have in this equation, we know that Cp is a constant, so that's given in the question. So Cpm is a constant. And what else do we know? In these equations, in both equations, we have alpha. And do we know what alpha is? Well, we have the definition of alpha. We have alpha equals to 1 over V over dV over dt at constant P. And in this equation, we have the equation of state. So PVM equals to RT 1 plus BP plus CP square. Or in this case, now I'm like, okay, so I should use the molar volume version of my alpha. That's all. So first step, listing everything that's mentioned in the question and see what are the tools we can use. All right. So what's the second step? So from there, in order to solve those integration, the second step will be, well, we want an expression of alpha by solving that differential equation. So let's do that together. So the second step is solving for alpha. Right, so my alpha is the partial differential of volume over temperature at constant P. So we know the equation of state. We can write my volume, molar volume, equals to RT 1 plus BP plus CP squared over P. We can solve for alpha. So my alpha thus equals to 1 over Vm, partial differential of over temperature of this entire thing. We have RT 1 plus BP plus CP squared over pressure at constant pressure. And I'm gonna skip my derivation problem, but this is just solving for alpha. You did that in the previous practice problems and everything, so you can solve alpha to be equal to 1 over T. Well, next step, calculating for delta H and delta S by solving these integral calculus. So my delta H equals to this Cp dt plus my V minus Td alpha dP. In the question, we're giving that Cp is a constant. So because the question says Cp is constant, we can take the Cp out to have my Cp delta T. All right, so we can do that only because the questions give us Cp is a constant. Or alternatively, I can also give you like Cpm equals to, let's say, RT, then it's gonna be a different integration. What about this term? Now alpha equals to 1 over T. That's what we solved for. You plug it in, you find out this term goes to 0. Or read it again, and I find, okay, the question is asking for the molar enthalpy change. So my delta H molar entropy change equals to delta H over N. So that becomes Cpm delta T. So far, so good. And next step, we have problem number 4, which is solving for my delta S. So that's your Cp over T dt minus alpha V dP. Again, plug in what we know. Cp is a constant, so I can take Cp out and solve for the integration of 1 over T dt. And minus my alpha times V. Alpha is 1 over T, but my volume is this entire thing. So we end up getting NR1 plus BP plus Cp squared divided by P dP. Right, because after all, we want to express my alpha and volume as some kind of function of pressure, so we can solve for that integral. All right, and then in here, what we end up getting, this one just gives me my Cp ln T2 over T1. This one is a little bit more complicated. Well, it's not hard, it's just integral calculus. And that's gonna be my NR times ln P plus BP plus 1/2 Cp squared from P1 to P2. Let's write it out. So if this question was like 25 points, or 30 points, let's put it this way, then 5 points will be just writing out all these expressions. And then this part would be another 5 points. Setting this up to be about like 5 points. And this one to be, again, 5 points. Right, and same thing. This one setting up the integral correctly by putting in the right thing, that's about 5 points. And actually solve it to the end, that's another 5 points. So for these kind of comprehensive problems, that's behind our logic when we're making these questions. Okay, any questions? We still have 5 more minutes and I'm running out of materials, so.
I was looking at just the general equation for alpha is equal to 1 over volume, partial V over partial T over holding pressure constant. And so that's kind of like normalizing the rate of change of the volume by dividing it by the volume.
Right, so this one goes back all the way to our equation of states. Remember, you have the Charles equation, you have the Boyle's law, right? So it's talking about how volume change with respect to temperature while keeping pressure constant. So it's something you can actually experimentally measure.
But like mathematically, it's kind of like normalizing the rate of change by dividing the rate of change by the entire volume.
Mathematically, I'm not gonna comment on it. I don't wanna say something that's wrong, so. Very good. So far, I hope this is gonna be a, one of those lectures, again, we're applying something we already know. Not only the thing that we derive, not only the Maxwell relations, but know when and where to use it, how to use it, how to link these thermodynamic relations with the equation of state to derive like a general expression to calculate for change of thermodynamic state functions. All right, so know how to use the equations, that's this lecture. Last lecture, know where the equations come from. But if we don't have any other questions, that's it from me today. This is the first time I'm on time for my physical chemistry. I'm like so happy. Normally I'll be like 2 lectures behind. I'm trying to catch up. Okay, I'll see you next lecture.